Euler's method. Euler's method is a way that we can estimate what an original function looks like. So to be clear, we've learned pretty much all the derivative rules there are to know. There's really nothing you can't take the derivative of. Integrals or antiderivatives, however, are a whole nother story. What we've learned so far in this class just scratches the surface, really. I mean, the rules we've learned are pretty powerful and pretty widespread. The more rules you learn, the kind of less that they apply to, but there's a whole lot out there that has just a whole lot of different methods, and there's even some things that you cannot take the integral of. And that's really what Euler's method is most useful for. That's not necessarily what we'll be using it for just for the sake of simplicity, but where it's really valuable is those equations that you literally cannot take the integral of. So, for those things you can't take the integral of, Euler's method offers a way to estimate what the graph of that original function would look like. So let me try to give you an idea. I'm going to draw a very poorly drawn river. I like how the banks are perfectly straight. And let's say the river's flowing this way, okay? And you've got a boat, and you're trying to get to this destination. Now, if you just push from the bank directly at the star, then what's going to happen is your boat's going to do something like this, because the current is pushing it. But if you push it one time and then you say, okay, wait a minute, we need to course correct, then you say, okay, wait a minute, we're starting to get off, we need to course correct again, and then you need to course correct again, you kind of get there. So in other words, if you do some course corrections along the way, you're a lot more likely to get to where you're going, or at least get closer to where you're going. And that's the idea behind Euler's method. We've done tangent lines before, so let me just draw this. Let's say we pick this point, we draw a tangent line. Okay, well I'd say, like, in this area right here, the tangent line's really not that bad of an approximation. I realize it's not curved, but it's pretty close to the actual values of our parabola. However, when you get like out here, it's pretty terrible. So the way we use Euler's method is we do one tangent line, but we only do it for a little ways, like say to there. And then we stop and say, okay, we need to course correct. So we start with this new point we have, and we figure out the slope, and we do a new one. And then we say, okay, we need to go there before we get too far off, and stop there and try another one. We do another tangent line, and then another tangent line. Now I realize that's still not perfect by any means, but it's much, much closer than that single tangent line we drew. And that's the idea behind Euler's method. You want to try to find points that will represent an approximation of our curve. And the key is that you're doing tangent lines. That's really the concept to hone in on, is you're doing tangent lines over and over. Okay, there's four things needed to solve with Euler's method. You need the differential equation, which is just going to be equivalent to your derivative, because we're using the derivative to estimate the original. We need the step size. That's just how far we go before we do a course correction. So that's how far we draw our first tangent line and our second tangent line and so on. And that's often represented by the letter h. And then we need to know how many steps to take. And then finally we need to know where we're starting, our starting point. Okay? So just to go back here and illustrate, our starting point was right here. Each of these would be our step size. That's how far we went each time. That's always an x value. We go over like 1 or 0.1 or 0.5 or something like that. And then here we took, let's see, 1, 2, 3, 4 steps. So I've got two examples for us to try. Here's the first one. The directions might say something like, use Euler's method to approximate the solution to this differential equation, starting at 0, 1 with a step size of 0.1, that's the h, taking 3 steps. Alright, so like I said, the goal here is to use tangent lines to find points that approximate the solution. Again, y prime equals x minus y, that's the derivative. We're trying to estimate what the original looks like. So I'm going to start over here and write 0, 1. So this is to the far right side of my paper if you're trying to follow along. And then this right here tells me I go up by 0.1 each time. So my next x value is 0.1, 0.2, 0.3. And I'm just doing 3 steps. So notice, your starting point does not count as one of your steps. You haven't gone anywhere. So you need to take 3 steps from your starting point. Now, like I said, we're trying to use tangent lines. So that's the equation we've been using in this course to find the equation of tangent lines. So that's what we're going to use here. I'm going to show you a slightly shorter way to do it, but just slightly, once we do this first example. But for now, we'll use this one. Okay, so here's the idea. y1 and x1 are the point we currently have. So right now we have 0, 1, so I would plug in 1 for the y1 and 0 for the x1. Okay, now I also want to find the slope. Well, remember, the derivative is the slope. So I take my point, 0, 1, and I plug it in this equation. So I plug 0 in for x and 1 for y. I get 0 minus 1, so my slope is negative 1. Okay, now my goal is to find this point right here. So I'm going to plug 0.1 in for x and then solve for y, because y is what I'm trying for. So I get y minus 1 equals negative 1 times 0.1. That gives me y minus 1 equals negative 0.1, or y equals 0.9. So my new point is 0.1, 0.9. Okay, and now I repeat the process using the new information I have. So I'm starting over, y minus, okay, my new y value is 0.9. I need to find my slope. So I take this point now and plug it in to the derivative. So 0.1 minus 0.9 is negative 0.8. Sorry about that. Our x value right now is 0.1, and we're trying to now find this point. So I plug in 0.2 for my new x value, and I'm trying to solve for my new y value. So let's go from here. We get y minus 0.9 equals negative 0.08. So you notice this part turns into just 0.1, so it's 0.1 times negative 0.8, so that's negative 0.08. Then we add 0.9 to both sides, we get 0.82. Okay, so now we have just one more to try. We have y minus, okay, again, you're updating with new information each time. So this is our newest point, so we plug this in for y and this in for x. So I get y minus 0.82. I'll find my slope in just a second. X minus 0.2. So y minus 0.82, x minus 0.2. If we plug this point, the 0.2, 0.82, back in up here into our slope equation, 0.2 minus 0.82 is negative 0.62. Sorry about that, my alignment's a little off. Negative 0.62. And the new x value I'm going for right here is 0.3. And then I'll use that to solve for my new y value. Okay? So if you notice, 0.3 minus 0.2 is 0.1 times negative 0.62, so you get negative 0.062. And then we add 0.82 to both sides. We get y equals 0.758. And that gives us our 3 steps. Okay, I'm going to scroll down so you can see the work again if you need to. So again, just to be clear, these points right here are my answers, or specifically the last 3, since those are the new points. 0, 1 was given. But that's the answer. If we were to plot that on a graph and then to connect the dots, that would give us an estimation of what the original function would look like. So just so you know, where this is particularly helpful is with computers. Computers can do this easily and all day long. You're just repeating this same set of steps over and over and over. And a computer can do this very quickly. So a computer could quickly do this for 100 steps, or 1,000 steps, or 1,000,000 steps. And the smaller you make your step size, the more accurate your answer is going to be. So a computer can easily do this for like 0.001 or 0.0001, and it's going to be a very accurate picture of what we have. Alright, now I want to show you how we can shorten this process a little bit. Okay, if you look back up here at our equation for a tangent line, well, if you look x minus x1 at all of them, okay, we got this here, I'll line it in red, we got this here, and this here. The answer to all three of those is 0.1. And the reason is our x values are going up in a predictable way because we're using a predictable step size. So instead of writing x minus x1, let's just write h, because that's what the difference in the x's is going to be. I mean, just look over here at your points. It goes from 0 to 0.1 to 0.2 to 0.3. So your x's are always going up by 0.1 each time. And that's going to be true. Whatever your step size is, that's how much you're going up in the x's. Alright, also, we're trying to solve for this y right here, so let's just add the y1 over to the other side. And this is the equation you should associate from now on with Euler's method. That's the equation we're going to use. So let's take this new equation and see how much quicker it can be on this example. So we're going to use y equals y1 plus mh. Our starting point is 3, 1. We're going down by 0.2 each time. So we'll go 2.8, 2.6, 2.4. Okay, so y1 is our newest y value, which is 1. I'm just getting that from right here. And then we need our slope. So I plug 3, 1 into the differential equation. So 2 times 3 minus 3 times 1 gives you, I think, 3. Let me just double check here. Okay, yeah, it's 3. And then our step size is negative 0.2. So I just do 1 plus 3 times negative 0.2, and I get 0.4. So that's my new y value. Notice we did the whole thing in just one line. Okay, so that's our first step. For our second step, we use our newest y value, which is 0.4, plus we plug our new point into our differential equation. So 2 times 2.8 minus 3 times 0.4, and we get 4.4 for our slope, times our h, which is negative 0.2. And we get negative 0.48. And we just have one more step we need to do. We plug in our new y value, negative 0.48, plus our slope. So we have to plug 2.6, negative 0.48 into our differential equation. So 2 times 2.6 minus 3 times negative 0.48 gives us 6.64. And then we multiply that by h. We get negative 1.808. And that's our answer. So hopefully you can see that y equals y1 plus mh is a lot quicker. The only reason I even made this do it with the other way with the first example is I wanted to drill the concept into you that what we're doing is tangent lines. We're really just using tangent lines over and over to find new points. Hopefully that's helpful for you. If you need any examples in our book, you actually have to go back to Appendix A on page A7, and there's some examples. I think the numbers are something like 8 to 14. They're in that range.